Is it recording? Okay, everyone, happy Friday. How are you? His number is going down. I think I should stop recording videos. By the way, Patrick is fired after the 13 minutes of silence from last, so Cesar is taking over. No, he's writing a paper. Everything is working fine? Okay. Sorry about that. I have a reminder I'm going to change the batteries every Wednesday. I think that's what I have. Even if it's an overkill, I don't want that to happen again. So hopefully that extra video I uploaded, and I did it by myself in the office, that covers more or less what I was saying. And hopefully I was making mistakes in that 13 minutes, so they're not on video anymore. So that was a trick. Okay, couple of things before we continue. So I don't know if I'm going to do circular, elliptical, parabolic orbits. We're right on schedule, so I thought I would finish what I was doing last time and use MATLAB again. I want to show you what I meant by you can use the Keplerian expression for the orbit, the one that we found, to plot the same thing that we plotted last time, integrating the equations of motion. I want to show you that that's a solution, because I can plot now a trajectory exactly like the one I gave you in MATLAB last time without even calling ODE 45 now, basing everything on H, E, and that through anomaly angle that we have defined, okay? But a few things. I received an email from one of you guys asking me basically questions about what chapters and sections we have covered so far. Now again, you guys are seniors, so I'm not going to respond to questions like that. As far as I'm concerned, the schedule is more or less laid out in the syllabus, and the titles for the main topics are also there, and the chapters where those things are also there. I think you're mature enough to open the book and figure out if I've talked about something or not. I just don't want to encourage people to skip stuff. What I tell you in class is what you should know. That's enough to go through the class and pass the tests and everything. But if you study more than what I tell you, there is no harm. So use the book, that's my point. Because some people, I think they just want to open the book when they are told go from page 1 to page 10, etc., etc. I'm not going to do that. So I don't want to be mean, but I think it's just harmful if I tell you what you can skip. Because I think you should know what you can skip. Chapter 1, for example. There is quite a bit of pages about numerical methods, and I said that I'm not going to spend any time on numerical methods because this is not a class on numerical methods, but it's there. Because some people may approach astrodynamics and have no idea about numerical integrators, so that's a pretty, complete book, but I'm not going to do anything about those because I'm assuming that you know them, and I'm not going to test your knowledge on numerical methods. So that's an example. And also, I am a filter between you and the book. I am a facilitator, that's the idea. So some things that are on the book are great the way they are. Other things I may just choose to explain them in a slightly different way because it makes it easier for me, or maybe because I think it makes it easier for you to understand. For example, the way the kinematics and dynamics are reviewed in that chapter, I don't like it that much, to be honest. And I actually done it in another way. Not that different, the concepts are the same, I just did it differently. I just thought I would underline that. Now so let's get going. One thing that I was not completely accurate about is this H vector. So at some point we said, okay, if we are sitting in the inertial frame and we look at mass M1, which is of course our planet as far as we are concerned, and M2, which is a spacecraft, we demonstrated that the H vector, so M2 is moving with some velocity relative, remember this is all relative now, to M1v, we demonstrated that the vector H is constant, right? It's H dot, so its time derivative with respect to n is constant. And so from that we said, okay, well that means that the plane here where R and V are contained is fixed. That is not completely true in the sense that this plane doesn't change orientation, but it doesn't need to be fixed with respect to the inertial observer. In fact, we have defined the ECI, if this is Earth now, M1 is Earth. We said I'm going to have a coordinate system with the center at M1 and the axes that are oriented exactly like, for example, the coordinate system which is fixed with the inertial observer, and I'm not going to let this axis rotate with respect to the inertial coordinate system. So in other words, if this is the ECI, the coordinate system fixed in ECI, Earth-centered inertial reference frame, the omega of, what do you want to call this? Let's just call it ECI. ECI with respect to n, we choose it to be 0. So in that particular coordinate system, which is centered at M1 and doesn't change orientation, then you can say that the plane is fixed. And that's all we care about. Now this mass, which again could be the Earth, could be actually moving, guess what, around the sun. Maybe, you know, the sun, like in the problem we solved together, is the origin of that inertially fixed coordinate system. So M1 can actually move. So M1 and M2 don't have to be fixed in a plane which is not moving with respect to the inertial observer, but we don't care. We said that a few lectures ago. We don't care about what they do with respect to the inertial observer. At some point, we just moved into this coordinate system here, or reference frame ECI, and in that case, I can lock that plane in place. Do we see the difference? We're looking at relative motion between two masses, and once we have demonstrated that we can sit in this coordinate system because the r dot is actually the relative velocity, and the r double dot is the relative acceleration, we have proven that in one of the lectures, then we forget about the inertial observer and we sit in this ECI frame. So in that one, the plane is really fixed, doesn't change. You can imagine that as a piece of paper, it's just always the same. While in n, well, its orientation is the same, but that plane can translate. Is this clear? We care about the relative motion between the two. And an additional way to prove that this is true is the following, transport theorem. What is h dot? What we computed last time. Well, this is by definition, because we agreed to use this notation, is d dt with respect to the inertial observer of the h vector. Guess what? This is also equal to d dt taken by the ECI observer of the same vector plus the omega of the ECI observer with respect to n crossed with h itself, but I've chosen this to be 0. So these two observers do see the same thing, which h dot is 0. So they both see that vector not changing. Okay? So that's another way to say that if the plane, if h is constant in n, is actually constant in ECI too. And that's why we've chosen ECI, which is again not inertial, but we don't care. We can use it for our goals, which is relative motion. Clear? Okay. This is my second post-it of the things I wanted to tell you. The last one is, well, we derived the Keplerian orbit expression, right? And we have to do a few more things with this. R is h squared over mu times 1 over 1 plus e eccentricity cosine of theta. This is the norm of a vector, so that e is always 0 or above 0. It's never negative. And to get here, we define the h and the e vector. I don't know if I want to reuse the same image here. Maybe I can. This e vector, I should start bringing different colors. You know, that would be a good. Yes.
I'm sorry. Can you explain real quick why it's 0 again from n to ECI? Because like you were saying that it's like the.
This one? We proved it last time.
Not that one. The omega.
I choose it that way. The way we define with the Earth sense. So if M1 is the Earth or another planet, it doesn't matter. We have said a couple of lectures ago that if you choose a coordinate system that has the origin in that attracting body and has the orientation that never changes with respect to the inertial observer, so I choose it that way. So on this planet, we use ECI, which is not a coordinate system that rotates with the planet. It has the center at the center of the planet, but the three axes are pointing at some faraway stars that we don't see really changing because they're very distant. So the axes don't change orientation. They are inertially fixed in terms of the orientation, but the center of that coordinate system can move. And we have proven that if we use this type of coordinate system, the r dot is actually equivalent to v, what was this, of mass 2 with respect to the inertial observer minus v of m1 with respect to the inertial observer, and also that r double dot is acceleration of m2n minus acceleration of m1n. This is only true if the omega is 0. So go back 2 or 3 lectures ago, I think.
Even though the Earth is going around the sun.
Yeah, the orientation of this frame, so imagine this is what the frame is doing, the coordinate system is doing. Doesn't matter what the center is doing, the orientation of the axis is the same, which makes it not inertial. Go back to that problem that we have solved, and it's a problem from the dynamics class. That's exactly what I was doing there. I was saying how good of an inertial approximation it is. Well, as long as the acceleration of this mass around the sun is negligible compared to the other accelerations that you measure, you're okay. But if the things that move with respect to m1 start accelerating with very small accelerations, then they become comparable. And that's probably not a good idea anymore. Okay, where was I? Oh, yes. So we define this h vector, and to get that equation, we define also, I don't know where it's oriented, this is just an example, this other e vector, right? And these two guys don't change. So to get to this, we have defined h, which is r cross with v, or r dot if you want to call it that way. And we said that this is constant, right? We also said that e, the eccentricity vector, is v cross with h over mu minus r over r. And this is also constant. Remember this? I hope that's the way I've defined E. I think it is. It's C over mu. Yeah. That's what we used. Now, another observation to make is, what if I now, and we also proven that these two are perpendicular to each other, right? I'm going to use this information when I open MATLAB at the end. Well, what about now we start thinking about using these two directions and then a third one as another coordinate system, right? I can use these 3 directions. This direction 1 points at some star down here. This direction 1 points at some other star, etc. You complete a right-handed frame, right-handed coordinate system. But would it be equivalent to use a unit vector that goes with h, a unit vector that goes with e, and some cross product that gives you the third direction? Would that be a legit ECI? What do you think? What is the only condition that I have imposed on that coordinate system? It's this one. It needs to be centered at the M1 location, and that's the only thing that I've chosen, right? So if I don't have the axis at the same orientation as whatever is the orientation of the inertially fixed coordinate system, I can orient them in another way as long as they don't change orientation, right? Omega is still 0. The angular velocity between two rigid bodies, or reference frames, doesn't have anything to do with lines that we draw that we call axes, coordinate systems. It's just that the two objects don't rotate with respect to each other. So I can choose anything I want here as long as it doesn't change orientation with respect to n, so its omega is 0. And that's what we're going to do. We're going to plot the trajectory of m2 with respect to m1 without integrating differential equations, using these and using these 2 directions to begin with as coordinate axes, because this plane is fixed. If I'm sitting on m1, this plane doesn't change. I see always m2 moving on the same plane, so I'm going to use that plane as a coordinate plane. Why not? I can do that, right? That is done all the time. And E describes, this is important, E describes what it's called. I'm going to start using some astrodynamics nomenclature here. It defines the UPS line, which, as we'll see in a second, it's really the axis of symmetry of these trajectories. Okay.
What is APS?
UPS. It's a word. I didn't invent it. So when you have, for example, the moon has a slightly elliptical trajectory. Everything is not, nothing is perfectly circular. I don't know what the eccentricity is. I don't remember it, but I think the closest point is called perigee, and the farther point is apogee, and they when you connect those 2 points, that's the UPS line, that's what it's called. So these trajectories that we see until they are closed.
There's just one out of focus that hasn't come back.
Really? It's dead. So this is perigee, this is apogee. This line here is the line of E, as we'll see in a second, and that's called the UPS line. Doesn't come back?
No.
Move it, just move it. Try to move it.
Already did.
Zoom out.
I did.
Yeah.
Maybe it'll come back.
Wow.
Oh,
Yeah.
there it is.
Yeah, you have to move it and zoom out. Play with it. It's an old one. Okay. That is true also for satellites. We call perigee and apogee artificial satellites, not natural satellites. We have one natural satellite, and that's the moon. And so even for artificial ones, we call apogee and perigee and UPS line the line that connects the two. And then we have periapsis and apoapsis for the Earth around the Sun, et cetera, et cetera. Yes?
So that line, it doesn't have to connect this. Does it have to connect to the center as well? The center dot that you have?
This is M1.
Okay.
Yep.
That's all three.
Yeah, let's make some comments on this expression here. I want to finish a few things. Last time we also talked about decomposing the velocity in a radial and tangential acceleration. Radial and tangential component. Now we also know that H is RV normal, right? Now if this is my E vector, which I have defined that way, and it doesn't change, and this is my R vector, and this is M1, and this is M2, and this is what I called, by the way, I didn't define this in the lecture without the sound, but in the additional one, I do give it a name. This is called true anomaly, the angle between the two. Does this configuration here, where you have a direction which is fixed, and then this vector that goes from an origin to another point that rotates with an angle theta, and the r can actually change, does it remind you of anything? Have I solved the problem in first or second lecture where that's what I had? That pipe that contained a point that could go also up and down in the pipe? That's exactly the same problem. So I'm going to skip to just say that the velocity of that M2 here, V or R dot, again, R dot or V are the same thing for us. That is going to be what? Well, again, it's V perpendicular, some direction U perpendicular, plus V radial, some direction U radial, which are these two directions here, and I keep having stuff in the wrong place. So this would be the UR radial direction, and this is my tangential direction. I know from that problem, actually, what do I know? That this is R theta dot, right? U perpendicular, and this is R dot, UR. You know, I may solve stuff in class that seem pointless at the time, but almost everything that we try to do has a meaning at some point. So this is exactly that problem. So now what do I do with this? Okay, this is my V perpendicular. So actually H can be expressed also as R times this. So what is it? R squared theta dot. And so from this I can solve that the rate of change of theta is H over R squared, and I'll just leave it there for now. And I'm going to find the expressions as a function of theta as well for the velocity, the radial and tangential velocity. Again, if I'm telling you that I can recreate the same plot I created with ODE 45 without integrating numerically the equations, that ODE 45 was creating positions and velocities. So I hope I'm able also to create the velocities in time or as a function of theta without integrating numerically anything. And that's exactly what I'm going to do. Okay. Let me see. What do I have? This. B perpendicular, just a scalar, is R theta dot. So it's H over R. Does it make sense? Right? It's theta dot times R. And if you recall, I'm going to rewrite it here. My solution for r is h squared over mu 1 over 1 plus e cosine of theta. So what do I get? H divided by that expression, bless you. What is it? Mu over h times 1 plus e cosine of theta. That's what I have. Yep, that's it. So that's another useful expression right here. You can tell me how far is the satellite from the attracting planet by changing the true anomaly. You can go from 0 to 2 pi. I hope it's clear that time is out of the picture for now. I don't know how that theta is changing with time. I completely removed time by introducing this parameter theta. I don't know how theta is a function of time. That will come. That can be solved as well. But I completely removed time. It's a completely parametric representation of the trajectory where theta is the parameter, right? Okay, what about the v radial? That is r dot. How do I handle r dot? I take this and compute r dot. What is that? Well, it's h squared over mu. That's a constant. Then I have, let's see, I have a minus 1 plus e cos theta. Now this becomes squared. And then I have the derivative of the denominator, which is minus e sine of theta. Is it still in focus, Caesar?
Yep.
The mic is moving?
Yep.
You never know. Okay. That's what I get, right? I know that theta dot, though, is... let's not rewrite the whole thing. Theta dot, I know it's h over r squared. So let's go through a few steps here. I have an h cubed here over mu. Fine. Then I have minus and a minus, they go away. Let's see, 1 over 1 plus e cos theta squared. Let me just put here e sine theta. Okay. And what am I missing? The r squared, right? Which is a denominator. So I take this and I square it, and I actually have to flip it. So I have a, let's see, what do I do here? Let me just open another parenthesis here. Mu squared over h to the 4th power, and then I have 1 plus e cos theta. The whole thing is also squared. So this goes away. A few other things go away. And so my final radial velocity as a parametric function of theta is mu over h e sine of theta. And this is another useful result. By the way, a good sanity check when you do things like this is, these are two velocities. If I had found here that this was an h over mu, I would be probably in trouble, because dimension-wise, they would not match. Okay, now, summarizing, I have all this information. What do I do with it? Well, I look at how these orbits are shaped. For example, my reference axis, I hope it's clear. If I am looking from above, so the h vector is coming out of the board here, right? I am looking down on this plane where everything is occurring, and I imagine to have m1 here, and this is my e vector, and I start counting the angle from e to go to r. Yeah, I don't know how long I want to make it. What are the few things that I can observe here? Well, that function, what is it, r? It's the only thing that is changing is the cosine, and the cosine is a symmetric function, right? If you go 0 to 2 pi, it's symmetric. So whatever happens from 0 to pi will repeat itself on the other side. Yes?
Sorry, what's the difference between these two pictures? Like, what was the big thing that we changed?
Nothing?
You said that the cosine was changing. Why?
I'm afraid I'm missing the question. I'm sorry. So what difference between which pictures? This and that picture?
Did you just say that, like, during this here, did you say the cosine would change?
Yeah, parameter is theta. Theta has to change, otherwise I haven't solved anything. So cosine is the only, what I said is that the only function here, the only part that is not constant, that it's changing is this, right? Everything else is a constant. H is a constant, E is a constant, E is a constant. So the only parameter that's changing is theta, and so it's cosine.
Sorry, I thought you meant it would change to sine.
No. Yep. So the only thing that is varying is this cosine, and as I said, the cosine is symmetric with respect to the angle. So the first thing that I can observe is that there is symmetry with respect to the ups line. That's why it's that line has a name. Try it. Just stick in theta 10 degrees or minus 10 degrees, you get the same R. So this trajectory, whatever it looks like, it's symmetric with respect to this direction. By the way, I hope we all know that vectors come in different flavors. There are vectors that are called bound vectors, like the position of a particle with respect to another one, where you really have to attach the origin of the vector to where m1 is, because R is telling me where m2 is with respect to m1. So those have to be attached to a point. Then there are other vectors that are free vectors. E is a free vector. I choose to plot it, in this case, I put it here attached to m1. It doesn't have to be there. I can put it somewhere else. It doesn't change anything. It's a free vector. You can move it parallel to itself. You put it wherever it's convenient, right? So I hope you don't think that there is an actual vector E that always has to be attached to m1. Not even R exists. It's something that we make up to call the position of m2 something, but R is really needed there. E is there because it's convenient for me. Okay, so are we convinced that this is symmetric? Whatever is the line that m2 is describing here around m1 is going to be symmetric with respect to that line. So you see on that side, you will see on this side. Then where is the closest point to m1? What is called the, around this planet, artificial or natural satellites, is called perigee. What is that? What is the smallest R you can get? You know? When is that happening? Again, for treat theta here, theta is your time. You can imagine that that's time. As it ticks, you're increasing theta, right? I don't know exactly how that relates to time for now, but when R equals E? When something along those lines, it doesn't ever probably equals E, but when it's in line with E, I would say, because the denominator of that is minimum when the whole expression R is minimized by maximizing the denominator, which is theta equals 0. And so that is, yeah, it's in line with E, h squared over mu, 1 over 1 plus E. Now, I hope you'll understand that as we move on to actual circular next week, the number of formulas that we'll come up with will explode. There's a lot of them, different flavors, you move things around. But it all originates really from having H constant and E constant and then manipulating them. I don't expect you to memorize a lot of stuff, but the key points, yes. Where they come from, yes. The same way I can compute the position at apogee. Where is that happening? Where I am as far as possible from cosine goes to as far away as possible. Is that as far away as possible? I can do better than that. I can do negative. For now, I'm not guessing anything on E. E can be anything from 0 to infinity, but you know, if we want closed orbits, it really needs to be from 0 to 1. But I can try to minimize the denominator, and that's at pi, right? 1 minus E. So h squared over mu, 1 over 1 minus E. Okay. interesting. So you are basically, I always have something in the wrong place. This is the E vector. So this will be your perigee. Again, there is no intent here to have anything to scale. I don't even know how long this is. I just have a vector here. But the closest point is here when theta is 0, and the farthest away is somewhere, you know, I don't know, this assume that this is an elliptical orbit. It's somewhere here at pi. It's on the other side. And what happens at, for example, the perigee? At the perigee, your velocity, radial, is 0. So the only thing you have is a tangential component, and it's whatever that is. It's mu over h 1 plus e. And as you go with theta increasing, your radial component of the velocity is positive, and it's going to lead you away from perigee. And it makes sense. If perigee is the closest point, when I go away from it, I should go to higher altitudes, to increasing r. So these are all very important geometric properties. What else do I want to tell you? There's one thing that we'll probably use at some point, and it's very quick to show. Any questions? So we have H, we have E. We can build a, no, we can look at the plane from the point of view of positive H. Just look down at the plane, and starting from E, we start counting with the true anomaly, and we know all these things already. Where I am the closest, where I am as far away as possible from the attracting planet, what the velocity looks like, all as a function of theta. One important parameter also may be the what is called the flight path angle. So I hope I can draw something that makes it evident. So this, let's say that this is part of your trajectory for M2, and you are here with M2. Your velocity vector is like this, and we said that we decompose it into a radial and tangential, right, component. V radial, V tangential, okay? This is your position R. Now, where this velocity vector is pointing is going to end up it's going to be very useful. For now, and for most of the class, this satellite here, M2, is a single point. In reality, that's an object. Your spacecraft is something that it's flying around the planet and probably has a camera down here and has to look down somewhere, for example, if that's its goal, or do something else. So where that velocity vector is pointing is kind of critical. If it's increasing the angle, the flight path angle, by the way, is this angle with respect to the local horizontal direction. So this is usually called gamma. And it's useful to be able to compute that as well as a function of theta. So how do I do that? Well, imagine V radial here and V tangential here. What is the relationship? V radial is V tangential tangent of gamma. So I have to do, I have tangent of gamma, which is V radial over V tangential, if I'm not mistaken. And so that ends up being E sine theta over 1 plus E cosine theta. So with this parameterization with theta, you can do whatever you want. You can find anything you need about the geometry of these orbits. Okay. Yes?
Is the radial velocity supposed to be a vector, or is that a scalar?
No, they're vectors, yeah. It's basically decomposing an existing vector in two directions, so they are the two.
One is also a
Yeah, they're both vectors. Yes. Yeah. Sorry. Yeah. Yeah. That is right. You want me to zoom in that ugliness up there? Maybe I should. Let me zoom in. This will be my V vector, and what I'm doing, I'm decomposing it into a V radial, okay, and a V tangential vectors, with the understanding that, of course, V radial is the direction of R, and V tangential is 90 degrees. Yeah. I tend to make small sketches. Tell me when I do, which is probably all the time. Okay. Any other questions? I have one more thing before I open MATLAB, and I want to show you how you can really plot many things without even thinking about ODE 45. No? Okay, one last ingredient, and then I promise next time we're going to start characterizing the different shapes and prove that these are conic sections, even though that expression is good enough as a proof. But we'll actually prove it in Cartesian coordinates that you get circles, elliptical trajectories, etc. The last piece that we need and we're going to use a lot is the mechanical energy of the orbit. That is actually what we are going to use extensively for maneuvers. When you want to change the shape of the orbit, circularize an orbit, transfer from a circular to a bigger circular, you're going to play with the energies of the initial orbit and the desired orbit so that you can compute what kind of changes in velocity, that is maneuvers, you need to implement. So what is mechanical energy? We know that it's kinetic energy, v squared over 2. Remember, this is all per unit mass, minus mu over r. So this is your kinetic energy, right, per unit mass. And this, we have proven it, it's my potential energy. We have proven, and this will give me the force model that I have when I take its gradient with respect to the r vector, right? That's the definition. What do I want to prove? I want to prove that this is also a constant for again, this. All this is coming from a simple model. If we don't have this model, everything I've done falls apart. So that's constant. So how do I prove that? D of E in dt. Do I need to say who's taking the derivative? Why not? It's a scalar, right? It's a scalar. So what is that? Well, let me rewrite this mechanical energy. I want to write it like this. R dot dotted with R dot, that will be v squared over 2 minus, the rest is the same, my mu over r. If I look at that and I take its rate of change, now this is a vector. It's dotted with another vector, but since it's a product, I have to take the rate of changes of each one and then multiply. Since I know that what I'm getting is a scalar, I can use any observer to take those rates of change. In other words, I'm going to use n as usual. So what I get is 2 r dot dotted with r double dot over 2. That's the derivative of the left component. And then here I get, what do I get? Plus mu over r squared r dot. Just a simple time derivative. I can do a little more here, which is this becomes my r double dot. I know that that's what's happening for the model of force that I have, of gravitational force that I have. So I'm going to substitute this. There's a dot here instead of r double dot. And then mu over r squared r dot. And I think we're done because we have proven that this dot product between r dot and r, or velocity and r, is also equivalent to just multiplying the norms of those vectors, right? So I'm going to change what I have here, and this becomes minus mu over r cubed r dot r plus mu over r squared r dot. Simplify one r here, and you get a 0. That's nice. So mechanical energy is also conserved on a Keplerian orbit. It's pretty useful. And I can, since it's conserved, the same way you can compute, bless you, h and e, and you do it once and for all. You just have some position and velocity at any time during the orbit. You can use those vectors to compute h and e, and you're done because they don't change. The same thing I can do with the mechanical energy, right? It's a constant. I compute it at any point, and I'm done. So how about I compute it at perigee? So I can do this. Velocity at perigee squared over 2 minus mu over position at perigee. Now the velocity at perigee was only tangential, and I have no idea what it was because I just erased it. Do you remember what it is? It's one of those two, right? Where is it? Perigee. This is radial, of course not the one I need. Okay. Velocity at perigee, I'm going to write it here. It's mu over h. Oh no, I have it. No, I don't have it. 1 plus e, right? Cosine is sine of theta is 0. I'm sorry, is 1. So that should be the velocity at perigee. The position at perigee is that. Let's see if we can do something with this. Let's square it. Mu squared over 2 h squared 1 plus e. The whole thing is squared. That's the kinetic energy. Minus, which is changing, by the way. These two pieces by themselves, they do change. It's the addition of the two that doesn't change. So the kinetic energy does not remain constant. This is at perigee. Minus mu divided by this, which means a mu squared over h squared 1 plus e. Right? Think so. Okay, let's collect a few things. Mu squared over h squared 1 plus e is multiplying 1/2 1 plus e minus 1. Mu squared over h squared. Do I have any errors here? Do you see any errors? You don't see any errors? Okay. What do I get here? There's something missing. I don't like it. I know what I need to get and I don't like it. Mu over h squared 1 plus e squared minus mu over rp mu squared h squared. That's right. So collect that. Okay. Maybe it is right. Yeah, it is right. Minus 1 over 2, right? Okay, so I can collect that 1 over 2 as well. So mu squared over h squared divided by 2. And here I have a 1 plus c times 1 minus e if I change the sign. So I get a 1 minus e squared with a minus in front. Okay. So what do I observe about this? Well, I can observe what the sign of this is, depending on the value of E. If, wow, should really speed up. What if E is 0? What do you get? It's negative. What if E is between 0 and 1 excluded? It's still negative. When E is 1 is 0. When E is greater than 1 is greater than 0. So for closed orbits, as we'll see next time, which is these two cases, you get negative mechanical energy, the way we have defined it. If you are moving on an orbit of 0 energy, you are on a parabola, which is that case, and then you have an hyperbolic orbit, which requires positive energy, and you go away. Any questions before I show you a few things? Yes?
With those different, is that similar to what application of energy you need to keep something over? Let's say, like, if I need more mechanical energy?
Yes. Yes. If you want to raise your orbit, you're basically making it less negative. You're trying to go towards more positive values. If you still want it closed, you still have to keep it negative. The moment you start having an open orbit, again, we'll see these things starting next week, you are not coming back. The moment you hit 0, you are on a parabolic orbit and it doesn't come back. Let me show you laptop. I hope my MATLAB still works. Do you guys have the same problem that you need to be on the network so the MATLAB works? Yes. I didn't have that before. Did you have it before? Yes. Yeah, 1 minus e squared. Yeah, I changed the sign. Yeah, sorry, yep. Oh, you can have it, yeah, either way. Why is it not showing? Oh, okay, duplicate, please. Okay, we have 5 minutes. I don't need to rush. How do I plot using that expression? Well, you define an appropriate coordinate system. And bless you, and I was mentioning that at the end of the extra video that I recorded. So now I'm sitting in the plane. H is sticking out of the board. E is some constant vector here. And I'm going to use E normalized as one of my coordinate axes. Then I have H normalized as one of my coordinate axes. So imagine this as the X. This is your Z. So if you want, I move it here, H. And then the cross product of the two gives me the third direction, whatever you want to call it. J. Okay, so this would be equivalent to an I, this would be equivalent to a K, and that's my J. And this is my orbital plane, and so my object here is going to be at a distance r, at an angle theta, and so my position vector r is nothing else than r itself cosine of theta on the E direction, the unit direction of course, plus r sine of theta on the j direction. Make sense? That's how you plot the same trajectory I gave you with the E45. So if MATLAB still works, of course it will not, I added this. So this was the same function you had before. I don't know if I'm going to give you this. I really want you guys to do it. This is what we were doing before with the ODE45, nothing new. I just removed the J2 part. If now I want to use that approach, I'm going to start defining my constant vectors H and E according to the formulas we have. You just have to do it with the elements you have, and the only thing I gave you was, that problem gives you, is the initial conditions. R0, V0. It's fine. Use those. H and E don't change. You can use those once and for all, and you have these two directions. And then I define a Z hat direction, which is the H direction. I normalize H. Then I define an X hat direction, which is the X, the eccentricity direction. And then the cross product of the two gives me the third direction that I need for a legit coordinate system. Now I have that coordinate system. What do I do? Well, my parameter is theta. With this instruction, I'm just creating a vector of theta values that goes from 0 to 2 pi with 360 points. So they are spaced 1 degree apart. It's just a choice. You can have more points if you want. And here I'm computing the norm of R at each one of those thetas. So these dots that you see, I'm sure you've seen them before, allow you to do a computation once and for all over a vector. Or you can do a for loop if you want. For 360 times, compute R according to the Keplerian orbit expression. Once again, R equals this. I really want to show you that you get the same plot. And then I create the vector according to that expression that I just gave you here. R is the norm times cosine of theta in the x direction, which is the eccentricity direction, plus r sine of theta in the y direction. So if I hit run and I plot the two, I am plotting, of course it's not going to work. Oh, it's going to work. Nice. I am plotting in red the one I was getting from ODE45. And I'm plotting in black, which you probably don't see that well, the one that I just created assembling that vector where there is no numerical integration at all. The only thing is that time is not the independent variable, it's theta now. And let me redo that. Control X. Just want to show you it's the same. So this is what I create with the parametric expression where I don't have any numerical integration. So one thing you want to do, I think is I strongly advise you to do, I don't think I'm going to share this piece of code with you because it's really simple instructions. Create the same orbit the way I've done it. This is the way I've done it. If you have any problems, you come see me. Because I can't give you every single MATLAB file that I develop. Otherwise, I will have nothing to give you for the homework. So, try and come see me if you have trouble. What is missing here? With ODE 45, I have more than the position. I have the velocity at each time. I am not creating the vectors of velocities, but you can do that as well. Do the vectors, though. V radial, V tangential, and then you have to combine them into a vector at each theta value. There are office hours. You can come see me. If you have any issues, maybe I'll spend a few more words next time, but I really want you guys to take this over because it's a good exercise. Okay, thanks.